Hello and welcome to this A-level chemistry video about amines. In this video we'll cover what amines are, how we name them and why we use them. From there we'll look at the different methods of preparing amines and then we'll explore the behaviour of amines both as bases and as nucleophiles. Amines are compounds based on ammonia, where one or more of the hydrogen atoms has been replaced by an alkyl or aryl group, sometimes pronounced aryl. So we could, for instance, have an NH2 group bonded to some kind of carbon-containing group, and we would represent this by the letter R. If the nitrogen is attached to a straight or branched carbon chain, it's called an aliphatic amine. And this is what we have here, where we've got the NH2 attached to a methyl group in this first molecule. In the second, it's attached to an ethyl group. And in the third molecule, it's attached to a propyl group. But if the nitrogen is attached directly to a benzene ring, it's an aromatic amine. And that's what we have in this diagram here. This is the representation of the benzene ring, and here is our NH2 group. And so basically an aliphatic amine comes from an alkane, whereas an aromatic amine comes from arenes, such as benzene. Now that we've seen the differences between aliphatic and aromatic amines, let's look at how we can classify amines as primary, secondary, or tertiary. The classification depends entirely on how many carbon chains, so that's alkyl or aryl groups, are directly attached to the nitrogen atom. A primary amine has one carbon group attached to nitrogen and two hydrogen atoms left. And we would show this generally as R bonded to NH2, where R is representing our carbon group. And you can see this in my first example, where I've got a simple methyl group attached to the nitrogen. And then in my more complicated second example, I have a cyclic alkane attached to the nitrogen. But this is still only a primary amine because there is only one carbon group attached. A secondary amine has two carbon groups attached to the nitrogen and one hydrogen remaining, and so it will be R2NH. And these two carbon groups could be the same, like here where I've got two methyl groups attached to the nitrogen, or they could be two different groups. A tertiary amine has three carbon groups attached to the nitrogen and no hydrogens attached to the nitrogen at all. And this is written as R3N. And my example that I'm showing first here has got three identical methyl groups attached to the nitrogen. But these groups could all be different, as I'm showing in my second example here. The key skill is recognizing that we don't count how many NH2 groups are in the molecule, and we don't look at the length of the carbon chains. We only count how many of those carbon chains are bonded directly to the nitrogen atom. 1 means primary, 2 means secondary, and 3 means tertiary. And this classification is important because it affects the naming of amines, and it also is linked to their reactivity as bases and as nucleophiles. The naming of amines can get quite complicated, so the process is usually slightly streamlined for A-level chemistry. For simple primary aliphatic amines, the name comes directly from the alkyl group attached to the nitrogen, followed by the word amine. So, for example, if the nitrogen is attached to a one carbon chain, that's a methyl group, the molecule would be called methyl amine. The same principle applies as the chain gets longer. 2 carbon atoms gives you ethyl amine. 3 carbon atoms in the chain gives propyl amine, and 4 carbon atoms gives butyl amine. All these are primary amines, remember, because the nitrogen is attached to only one carbon atom. If the nitrogen is attached to a benzene ring, that's an aromatic amine, and the name is phenylamine. And this is because the benzene is considered to be a branch substituent, and so the name is changed to phenylamine. We also name secondary and tertiary amines quite simply when all the alkyl groups are identical. And so if we had a nitrogen atom with 2 methyl groups attached, this would be a secondary amine called dimethylamine. And if there were 3 methyl groups attached, this would be a tertiary amine, and it would be called trimethylamine. And so this has the same idea as naming lots of other organic compounds. The prefix tells you how many groups there are, and the alkyl name tells you the group's identity. Things get a little more complicated when the groups attached to the nitrogen atom are different. In these cases, we need to show which of the groups are directly bonded to the nitrogen by using the prefix N as a position indicator. To do this, we need to decide which is the parent amine. In other words, which amine has the longest chain length. And then any other alkyl groups attached to the nitrogen atom are written as N substituents. In other words, we're using N as a position indicator instead of a number. And so here we've got a nitrogen atom with an ethyl group and a methyl group attached. And so ethyl is the longest chain, and so this would be ethylamine. But the methyl group that's also attached to the nitrogen means that this should be called N-methyl-ethylamine. And in this second similar example, we've got a methyl group and a propyl group on the nitrogen. And so the longest chain is the propyl, so this is propylamine. And the methyl group is also on the nitrogen, not anywhere in the propyl group. And so we would call this N-methyl-propylamine. Amines can also be considered to be substituents on a carbon chain when there are other higher priority functional groups attached. In this case, they are considered to be amino groups that branch off from the main carbon chain. One example of this is the molecule that I'm showing here that has 2 functional groups, the amine group and an aldehyde group. The aldehyde group has the highest priority, so this would be, first and foremost, an aldehyde. Its chain length is 4, so this would be butanal. The presence of the amine group means that this will be an amino branch. The aldehyde functional group is given position number 1, so the amine group is on carbon atom number 3, and so this would be called 3-amino-butanal. A second example of this is the amino acid alanine, which has a carboxylic acid functional group and the amine functional group. Carboxylic acids have the higher priority, so it will be something anoic acid. The carbon chain length is 3, so it will be propanoic acid. The carboxylic acid group is given position number 1, and the amine group is on the second carbon along, and so this would be 2-amino-propanoic acid, which is what you would need to write if you were asked for the IUPAC name of the molecule rather than being allowed to just call it alanine. Amines can be synthesized in a variety of different ways depending on which class of amine you're trying to make. Aromatic amines, such as phenylamine, can be prepared by the reduction of nitro compounds using a tin catalyst and hydrochloric acid. To make the nitro compound, you would first react an arene, such as benzene, with concentrated nitric acid and a concentrated sulfuric acid catalyst. And this would produce nitrobenzene in an electrophilic substitution reaction. Then, to reduce the nitrobenzene, you'd add the tin and the hydrochloric acid. In an equation, you can write the reducing agent as a capital H inside square brackets. This reducing agent does 2 things. Firstly, it reacts with the 2 oxygen atoms in the nitro group to produce 2 molecules of water, and the reducing agent also reacts with the nitrogen atom to form the amine group. And so overall, we need 6 hydrogen in our balanced equation. The variety of aromatic amines that can be produced in this type of reaction are used in the manufacture of dyes, more specifically very brightly coloured dyes known as azo dyes, which are characterised by having this type of group of nitrogen atoms connecting several benzene rings together. We can prepare aliphatic amines in a two-step synthesis starting with a halogenoalkane. This method makes primary aliphatic amines, where the final step of the preparation is the reduction of a nitrile. We can prepare our nitrile through nucleophilic substitution of a halogenoalkane using KCN dissolved in a solvent that is a mixture of water and ethanol, or you could say aqueous and ethanolic. The equation for this reaction could have bromoethane reacting with KCN, and we would produce a nitrile, which in this case would be propane nitrile and also KBr. To carry out the reduction, we would add hydrogen and a catalyst that would typically be nickel, but could also be platinum or palladium. The equation for this reaction has our propane nitrile reacting with two molecules of hydrogen to produce, in this case, propylamine. In this process, no further reaction can occur, and therefore we get a single product, our desired primary amine, and so the reaction will have a very high atom economy. However, this method can only produce primary amines, not secondary or tertiary, and it lengthens the carbon chain. So bromoethane is converted into propane nitrile, and we couldn't use this method to produce ethylamine from our bromoethane, as the carbon chain is always getting longer by one atom of carbon. Another disadvantage of this method is that it requires a two-step synthesis, and so this could potentially have a much lower percentage yield than a one-step synthesis. We can prepare aliphatic amines by reacting ammonia with halogenoalkanes. One advantage of this method is that we make an amine after only one step, and so this step itself will have a high percentage yield. The reaction is a nucleophilic substitution mechanism, where we start with our halogenoalkane, for instance bromoethane, and we react it with two molecules of ammonia, and we produce our amine, which would in this case be the primary amine ethylamine, and we also produce ammonium bromide, which is a salt. When we use an excess of ammonia, the major product will be a primary amine. A potential problem with this method, though, is that the amine produced can act as a nucleophile because it has a lone pair of electrons on the nitrogen. And this means that even with an excess of ammonia, further substitution can occur. And so this reaction leads to the production of primary, secondary, and tertiary amines, and potentially quaternary ammonium salts. This means that we're likely to produce a mixture of all of these chemicals, and so we will make an impure product, which is not ideal if we only wanted to make the primary amine, as the percentage atom economy is likely to be low. However, if we wanted to produce the secondary or tertiary amine or the quaternary ammonium salt, this is the method that we have to use because it allows us to produce these more substituted amines. And we could try to prioritize the production of these amines by using an excess of our halogenoalkane instead of an excess of ammonia. One of the properties of amines that you need to know about is their ability to act as bases. Bases have various definitions, and the most relevant here are that bases can act as proton or hydrogen ion acceptors and also as lone pair or electron pair donors. Amines are bases since they contain nitrogen atoms that have a lone pair of electrons that can accept a hydrogen ion. They are only weak bases since the lone pair on the nitrogen is often less available to accept a proton than it is on, say, a hydroxide ion. And so the reaction with an amine accepting a proton is often an equilibrium. For example, if we reacted propylamine with water, we would get an equilibrium which produces a protonated amine and hydroxide ions. And this would show a colour change with an indicator. For instance, we would see a blue colour with universal indicator. With a stronger acid, for example hydrochloric acid, this reaction would go to completion and the amine would be fully protonated. For example, if we took ethylamine and reacted it with hydrochloric acid, we would produce ethyl ammonium chloride, an ionic salt that would be soluble in water because we've got the negative chloride ion and the positive ethyl ammonium ion. The base strength of an amine is always compared with ammonia, and so ammonia is in the middle in terms of base strength. When an amine acts as a base, its strength depends on its ability to use the lone pair of electrons on the nitrogen atom to accept hydrogen ions. In aliphatic amines, such as methylamine that I'm showing here, the alkyl group is electron releasing, and this means that it is effectively letting the nitrogen atom take a larger share of the electron pair in the covalent bond. And we call this the positive inductive effect. And this doesn't happen in ammonia, as it's just 3 hydrogen atoms bonded to the nitrogen. And this means that the lone pair of electrons on the nitrogen is most available to accept hydrogen ions in an aliphatic amine. And so they are the strongest base. And the lone pair is least available in aromatic amines, and so these are the weakest amine base. In arenes, such as benzene, 1 electron from each carbon atom is delocalized to form a pi cloud of 6 electrons. In the aromatic amine phenylamine, the lone pair is in a favourable geometry to join the delocalized pi cloud. And so we can say that the lone pair of electrons on nitrogen is delocalized into the pi cloud of the benzene ring. And this means that the lone pair of electrons on the nitrogen is now less available to accept a proton, and so, therefore, it will be a weaker base. In aliphatic amines, when there are more alkyl groups attached to the nitrogen in the amine, there will be more alkyl groups that are electron releasing, and so there will be a greater positive inductive effect. Remember that the strength of a base depends on the availability of the lone pair of electrons on the nitrogen atom. And so the greater the positive inductive effect, the more available the lone pair, the stronger the base will be. And this means that a tertiary amine with 3 alkyl groups attached to the nitrogen atom will be a stronger base than the secondary amine with 2 alkyl groups attached to the nitrogen, and the secondary amine will be a stronger base than a primary amine with only 1 alkyl group attached to the nitrogen. So the key point is that it isn't the identity of the alkyl group that matters, it's the number of alkyl groups on the nitrogen, because it's this number that influences the availability of the lone pair of electrons. Amines can act as nucleophiles, which means that they're able to act as electron pair donors. When nucleophiles react, they use their lone pair of electrons to form a new bond to an electron-deficient atom, which for A-level chemistry will normally be a carbon atom. Carbon atoms will be electron-deficient if they are bonded to at least one highly electronegative atom. For example, we see this when a carbon atom is bonded to a halogen atom, for instance, chlorine, in halogenoalkanes. Since chlorine is much more electronegative than carbon, the electrons in the covalent bond are pulled closer to the chlorine atom, making that atom partially negative, or we might say electron-rich, and the carbon atom is partially positive or electron-deficient. In acyl chlorides, the carbon atom is bonded to two highly electronegative atoms, the chlorine and the oxygen, and so the carbon atom will be even more electron deficient than in the halogenoalkane. There are two main mechanisms for amine reactions that we're going to look at, and these are nucleophilic substitution and nucleophilic addition-elimination. For the nucleophilic substitution mechanism, the most commonly tested example is when ammonia reacts with halogenoalkanes to form primary amines. This reaction happens because of the polar bond in the halogenoalkane. Since chlorine is more electronegative than carbon, the electrons in the covalent bond are pulled closer to the chlorine atom, which makes the carbon atom electron deficient, and so it is attacked by the ammonia nucleophile. The nitrogen atom in the nucleophile uses its lone pair of electrons to form a new bond with the carbon atom. And at the same time as this, the bond between the carbon atom and the chlorine atom breaks, and the chlorine atom takes both of the electrons from the bond. This produces these two intermediate chemicals. Firstly, the chlorine atom is now a negative chloride ion, as it took both of the electrons from the bond with the carbon. And the nitrogen atom of this second intermediate is positively charged, because it has shared its lone pair of electrons with the carbon. To become neutral again, the nitrogen atom needs to break one of the bonds it's sharing with a hydrogen atom and take both of the electrons for itself. Hydrogen ions are too small to be stable as a positive ion by themselves, so they need a base to remove them. And the base in this case is a second ammonia molecule. You're not normally required to show this curly arrow, but if you do, it needs to be an ammonia molecule removing the hydrogen atom. And this is because we normally carry out this reaction with an excess of ammonia. After this step, we get our final products, which in this case would be methylamine and ammonium chloride. The overall equation for the reaction would have the chloromethane reacting with two molecules of ammonia and producing methylamine and ammonium chloride, with the first ammonia in the reactants acting as the nucleophile and the second ammonia molecule acting as a base. During nucleophilic substitution with ammonia, further substitution can occur because the products are primary, secondary or tertiary amines, and these have a lone pair of electrons. So if we produce any of these in a nucleophilic substitution reaction with a halogenoalkane, then these amines will behave as nucleophiles and further substitution will occur. This can happen in any reaction, but they are particularly common if we use excess of halogenoalkane instead of excess ammonia. So a primary amine can act as a nucleophile and attack the electron-deficient carbon of a halogenoalkane and form a new bond to it using the lone pair of electrons on the nitrogen. The carbon to chlorine bond will break, leaving us with these intermediates. Again, the nitrogen atom is positively charged, and so a nitrogen to hydrogen bond will break, and we will make a secondary amine product. On this occasion, since we're using an amine, not ammonia, the base that removes the hydrogen from the intermediate would be an amine molecule, and we would form an ammonium salt, methyl ammonium chloride in this case. And so this time the overall equation has the halogenoalkane reacting with two of the primary amine, the first of which does the nucleophilic substitution and forms the secondary amine product, and the second primary amine in the reactants acts as a base and forms the salt. This secondary amine still has a lone pair of electrons on the nitrogen, and so this process repeats, and we will produce a tertiary amine and a salt. Finally, this tertiary amine product still has a lone pair of electrons on the nitrogen, and so it can undergo nucleophilic substitution one last time to produce a quaternary ammonium salt. This process results in a mixture of products forming, the primary, secondary and tertiary amine, as well as the quaternary ammonium salt. And this mixture can be separated by carrying out a distillation reaction. Quaternary ammonium salts can form in nucleophilic substitution reactions where there is a large excess of the halogenoalkane. The equation for the final step would have the tertiary amine reacting with the halogenoalkane to produce the quaternary ammonium salt and no other product. The displayed formula for this example would look like this, with 4 methyl groups attached to the nitrogen atom and the whole structure being labelled as positively charged, or you could put the plus sign on the nitrogen atom itself. Because of the 4 methyl groups attached to the nitrogen, the name for this compound is tetramethyl ammonium chloride. You can sometimes be expected to draw the skeletal formula for quaternary ammonium salts, and they can start to look quite complicated, as you can see from this example that I'm showing here. Quaternary ammonium salts are often used as cationic surfactants, which are often used for various cleaning applications such as fabric softeners, hair conditioners, and disinfectants. This works because quaternary ammonium salts contain a positively charged ammonium head and long hydrocarbon tails. The charged head is attracted to water, while the non-polar tail dissolves in grease, and so the quaternary ammonium salt sits at the surface and helps to lift the oily dirt away from whatever surface you are cleaning. The nucleophilic addition-elimination mechanism occurs when there is a reaction of the carbonyl group in one of a number of chemicals, and these are acyl chlorides, where there is a chlorine attached to a carbonyl group, acid anhydrides, where there is a second carbonyl group connected to the first by a bridging oxygen atom, and an ester, which has got the carbonyl group connected to an oxygen and then a carbon chain. You can recognise that a nucleophilic addition-elimination mechanism will occur when you see that it's a reaction of the carbonyl group in one of these 3 chemicals. What actually happens in a nucleophilic addition-elimination mechanism is a positive-seeking substance, the nucleophile, attacks and joins onto the carbonyl carbon atom, which will be electron deficient. And so this is the addition stage of the mechanism. And then the elimination stage of the mechanism is where part of the original organic molecule then leaves. This mechanism occurs because the carbon in the carbonyl group is electron deficient, and this is because it's actually connected to 2 electronegative atoms, the oxygen and sometimes another oxygen or a chlorine. Both of these atoms are more electronegative than the carbon, so they pull the electron density from the covalent bond towards themselves, leaving the carbon delta plus and the oxygen and the chlorine delta minus. And so the nucleophile attacks the carbonyl carbon and forms a new bond to it. As well as knowing which organic molecules will undergo nucleophilic addition-elimination, you can also recognise that this mechanism might occur depending on the nucleophile. There are 4 that you need to know about. First of all, we've got ammonia, which has got the lone pair on the nitrogen, which enables this to act as a nucleophile. We've also got amines, which also contain nitrogen, and we can have a carbon group of any different length. And then we've got water, which has got the oxygen, which has got the lone pair that enables this to act as a nucleophile. And then we have alcohols last of all. Normally, we would see methanol as the nucleophile. Since this video is focusing on amines, I'll use the first 2 nucleophiles as my example, and I will have them attacking the acyl chlorides, which is by far the most common organic molecule for the nucleophile to attack. Acyl chlorides react vigorously at room temperature with ammonia. And so if I had methanoyl chloride reacting with ammonia, the first step of the mechanism would be the ammonia donates its lone pair to form a new bond to the carbonyl carbon that it was attracted to because that carbon was electron deficient. And then the oxygen takes 2 of the 4 electrons from the double bond that it shared with that carbon atom, and this produces our intermediate, which has got the nucleophile now connected to the carbonyl carbon, and the nucleophile will be positively charged because it's used its lone pair to form a new bond. The oxygen that was part of the carbonyl group originally is now going to be negatively charged because it took 2 electrons out of that double bond, and it needs to be shown as a separate lone pair now on the oxygen. And then I'm showing one of the bonds between the nitrogen and the hydrogen as being separate, and I'm showing it on display because what's going to happen now is that bond is going to break and the nitrogen is going to take both of the electrons from the pair. You can see that I've drawn my nitrogen and hydrogen quite close together, so I'm exaggerating this curly arrow to make it really obvious that it's starting from the bond and finishing on the nitrogen atom. In addition, we remake our carbonyl double bond because that lone pair goes back into the area between the carbon and the oxygen, and we get a new bond forming, and the chlorine takes the electrons from the bond that it shared with the carbon, and that leaves and it is eliminated along with the hydrogen. And so the HCl is eliminated from this molecule, and then the acyl chloride derivative produced in this instance would be an amide because the ammonia has formed on the same carbon as the carbonyl group, and so we've now got a carbonyl group and an NH2 on the same carbon, and this is the amide functional group. And you name amides by simply having methan, ethan, propan in front of it. And so since I was using methanoyl chloride in my example here, I would produce methanamide. And we can use an equation to represent this reaction as well as a mechanism. And so this is the structural formula of methanoyl chloride, and it's reacting with ammonia, and we produce our methanamide, and the HCl is eliminated, and we would observe misty fumes. And with acyl chlorides, the second product is always HCl, so we would always observe these misty fumes of the toxic HCl gas. Acyl chlorides also react vigorously at room temperature with primary amines, and the mechanism is identical to when ammonia reacts, but we produce something different in this case. And so the first step is the attack of the nucleophile on the carbonyl carbon. That lone pair forms a new bond between the nitrogen and the carbon, and the bond between the carbon and the oxygen partially breaks, with the oxygen taking both electrons from the bond. Then we produce our intermediate, which needs to have a negative charge on the oxygen and that lone pair, and the nucleophile is now attached to the carbonyl carbon, but it will be positively charged because it's used its lone pair to form this new bond. And so in stage 2, the bond between the carbon and the chlorine breaks and the chlorine leaves, and the oxygen uses that lone pair to remake the bond between the carbon and the oxygen, and that now becomes a double bond again. And from within the part of the molecule that was the original nucleophile, the positive charge is stabilized because the nitrogen takes the pair of electrons from the bond that it shared with that hydrogen, and the hydrogen is eliminated as an H+ ion. And so we produce this organic product, which would be referred to as an N-substituted amide on this occasion. And so it's called this because we've got something that looks really similar to an amide. If this CH3 group wasn't there and was an additional hydrogen instead, this would be an amide. But because we've got a methyl group, it needs to be a substituted amide. And because the methyl group is attached to the nitrogen, we use the nitrogen as a position indicator, just like we might a 1, 2, 3 in a complicated name. And so an N-substituted amide has got a carbon chain attached to the nitrogen. So in this case here, when we're naming our N-substituted amide, we should always name the amide part first. And so we've got a carbon chain of 2, so this would be ethanamide. But we've got a methyl group attached to the nitrogen as well, and so this would be N-methyl ethanamide. And remember, we make our two ions as a product, which would come together to make HCl. So we would refer to this as having eliminated HCl from the molecule. In terms of an equation, we've got our ethanoyl chloride structural formula here. It's reacting with the methyl amine, and we're producing our N-methyl ethanamide and the HCl. Okay, that's the end of this video. Thanks for watching.